Hi everyone. This is our second last lesson, and our final two lessons focus on finding trends within groups of data, specifically known as linear and nonlinear regression. So linear regression, okay, is looking for a line of best fit or straight line or a straight line that best fits this data. Okay, so these can be used to show, a line of best fit showing, that in general, your data increases as your value of x increases, or showing the opposite and showing that maybe it decreases as your value of x increases. Okay, so these are called line of best fit is what I refer to them as. In your textbook, you'll also see it called the least squares line. And the reason it's called that is that the method we're going to use, which creates the associated formulas, is known as the method of least squares. Okay? What this does is we're creating a line. So picture this example here. We have a line here. This is the line of best fit for this data. Okay? What this does is it looks at the difference between the y-coordinate of each point and its associated y-coordinate on the line of best fit. Okay, so at the same value of x, okay, the x-axis is left to right, the y-axis is up and down. So it looks at that difference, okay, so this piece here, which is known as the deviation, and it finds the location to place the line so that when you add up all of those deviations, it's as small as it can be. So it's the minimum it could be for that given data set. In other words, that line is as close as possible to all of the given points in the graph. Okay? So like I said, this is a line. Okay, it's a straight line. In our next lesson, we're going to talk about nonlinear regression, where the line will not just be straight. Okay? So this line starts with an equation that all of you have probably seen one or more times in your math endeavors. And it's the basic equation for a line, y equals mx plus b, where x and y are the coordinates for each point on the line, right? So each point that I'm drawing here in red would have an associated x and y coordinate. Okay? And they fit into this equation. M is the slope of that line. In other words, how steep this line is. Where you may have seen it written as is delta y divided by delta x, or it's the ratio of the change in y to the change in x. You also might have seen it written as the rise divided by the run. Okay, so the rise over run being how far, rise being up and down, divided by the run, which is left to right. Okay, so it forms this kind of triangle. That determines how steep or shallow this line is. So for instance, okay, a line that looks like this would have a larger slope or m value than this line here. Similarly, I'll change colors. A line like this will have a smaller slope value, okay? Because its rise divided by its run, or its change in y over change in x, okay, is smaller. So it doesn't change much in the y direction or up and down compared to how it changes left to right. Okay? Our last point, b, in this equation is the y-intercept. And that is simply, okay, looking at this, this is the y-axis. It's where it crosses the y-axis. Okay? So for this green line, it's right there. For this blue line, it's right there. And for this red line that I drew, if you continue this down, that's the wrong color, I'm going to switch to red. If you continued this down, okay, it's somewhere down here. So it's quite simply where it crosses that imaginary kind of y-axis point. Okay, so this is our starting point, and it's our starting point for both linear and nonlinear regression. The key here is we are going to use this exactly the same as you would have learned how to create this equation for a line. Okay, the only difference is the formulas for m, the slope, and b, the y-intercept, are far more complicated. Okay, so I don't want you to look at these formulas and instantly be intimidated if you've never seen linear regression. But these formulas are what I mean when I say it looks at this difference, okay, between the points. And it tries to minimize that, okay? And it does that by looking at 4 different things, okay? It looks at the sum of all the x coordinates, all of the y coordinates, x and y multiplied together, and x squared. Okay, so your sum of x terms, you can see them here in red. In your y-intercept, you can see it here. Okay. Your sum of y terms, I'll do in a different color. You see them here and here. Our x squared terms, here, here, and here. You'll notice these are different. These are the sum of x and then that value squared. Okay, so they're different. And our last term, well, it was our last term, sum of x squared. Okay, so it uses all of that data, which is data we have to compile manually when we're doing it by hand, to find the slope and y-intercept that best fits this group of data. Okay, so our formulas are the slope is equal to n, which n is your just total number of data points. Okay, so that's x and y. Okay, so if you had x and y like this, and you had 1, 2, 3, and your y coordinates were something like 4, 10, and 16. This is considered n equals 3 because there's 3 sets of data points, x and y here, here, and here. Okay, picture that, I guess, is kind of like a word search. So you've got 3 sets of data. I don't want you to get that confused and think that you have 6 data points, right? A point on this graph is an x and y coordinate placed together. Okay, it's not just an x coordinate and it's not just a y coordinate. So your slope is the number of data points times the sum of x times y minus the sum of x times the sum of y divided by n, the number of data points, times the sum of the x squared values minus the sum of x, that value squared. Okay, so those are different terms. It's very important. Your y-intercept is a similar formula. In the numerator, it's the sum of the x squared values times the sum of y values minus the sum of x, y multiplied together, all of those values, times the sum of all the x terms. And it's divided by the same denominator as the slope. Okay, the number of data points times the sum of the x squared terms minus the sum of the x terms, that value all squared. Again, remember, that's very important, okay, to keep that in mind for that term. Okay, so these seem like they're complicated, but you just have to compile the data properly, and you'll see that I have tables on my next 2 examples to walk you through this. Okay, so we're going to look at doing examples by hand. You might have seen in the first slide of this that I noted part 1. The reason for that is we are going to then, in part 2, I'm going to show you how to create these lines of best fit and display their actual equation on Microsoft Excel. Okay, so to see how to use it, practically, you're not going to do these calculations by hand practically. You're going to put them in Microsoft Excel or some equivalent program to find this line of best fit. Okay, so I'm going to show you both methods. All right, so our first example, you might have seen this image, it's the one I've been drawing on. It's a figure from your textbook. You'll notice a lot of these are all figures from your textbook that I'm using. And to find the line of best fit for the image I keep using from the textbook. And I'll give you a set of x and y values. So x is simply 1, 2, 3, 4, and 5. Your y values are 3, 6, 6, 8, and 12. So remember, the items that you're looking for were the sum of the x terms, the sum of the y terms, the sum of the x times y terms, and the sum of the x squared terms. So I provided this table here where we're just simply going to write these values in. X is 1, 2, 3, 4, and 5. This last row will be for our sum. Our y terms are 3, 6, 6, 8, and 12. So x times y, in this case, we can do each of them by just multiplying them together. 1 times 3 is 3, 2 times 6 is 12, 3 times 6 is 18, 4 times 8 is 32, 12 times 5 is 60. Our x squared terms, we have 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, and 5 squared is 25. Now adding each of these up, the sum of your x terms, adding up all the terms, okay, I'm going to do this for all 4 columns. Sum of the x terms is 15. Sum of the y terms is 35. X times y terms is 125. And the x squared terms is 55. And that's simply just adding up those numbers. Okay? So with that, okay, knowing these sums, we can now find our slope and our y-intercept. Okay? So our slope, m, is equal to n, the number of data points, which I have to explain, or we'll count in a second, times the sum of x times y, minus the sum of the x terms times the sum of the y terms, divided by n times the sum of all the x squared values, minus the sum of all the x terms, all squared. Okay? So the term we don't know, n, so in this case we have 5 sets of data points. 1, 2, 3, 4, and 5. So n in this case is equal to 5. Substituting all these values in, we get m is equal to 5 times the sum of x times y, which is 125, minus the sum of all the x terms, which is 15, times the sum of the y terms, 35, divided by 5 times the sum of the x squared, which is 55, minus the sum of the x, which is 15, all squared. So if you multiply this out, you get 100 in the numerator and 50 in the denominator. 100 divided by 50 gives you a slope of 2. For our y-intercept, b, we do the same thing. Sum of the x squared values times the sum of the y values, minus the sum of x times y terms times the sum of the x terms. That's divided by the same denominator. So n times the sum of x squared terms minus the sum of all the x terms squared. Okay? So for b, that means it's equal to the sum of the x squared terms, which is 55, times the sum of the y terms, which is 35, minus the sum of the x times y terms, which is 125, times the sum of all the x terms, okay, which is 15. And that's divided by 5, the number of data points, times the sum of the x squared terms, 55, minus the sum of the x terms, 15, all squared. You multiply this out, you get 50 in the numerator and 50 in the denominator. So notice these values are the same, and that's because it's the same term in the denominator. Okay, so keep that in mind. You should get the same answers. So your value for b is 1. So what that means is, remember our initial equation is y equals mx plus b. So y is equal to 2 for the slope times x plus 1. Okay? So that actually is this line shown in this figure, y equals 2x plus 1. So you can see here that our value for the y-intercept is 1. Okay, you can see that point that I noted. And for each change, 1 in the x direction, we go up 2 in the y direction. Okay, so that's what it means by a slope of 2. All right, so you can see that that's actually what they've graphed here. Okay, just to show you what it means when you see it kind of in a picture like that. So our second example is find the line of best fit. Again, I wrote it in here that it's also called in your textbook the least squares line for the following data. So in this case, we have temperature and pressure, temperature in degrees Celsius, pressure in kilopascals, kPa. So I don't note these as x and y, but what you'll see here is when you're graphing these, x is an independent variable, so the temperature just is what it is, 0, 20, 40, 60, 80, and 100. So that must mean that temperature is the x coordinate. The y-coordinate pressure depends on the temperature. It's what's known as a dependent variable. So that means your pressure is your y-coordinate. Okay. So I've put the same table in here. Okay, I've just added an additional row because this actually has 6 pieces of data that you'll see. So when we start off, remember our equation is y equals mx plus b. And after we fill in this table, the other piece we need to know is how many data points we have. Okay, so we have 1, 2, 3, 4, 5, and 6. So our value for n is 6 data points. Okay, so now we'll fill out this table before we calculate the slope and the y-intercept of our line. So for x, we're going to put our temperature values 0, 20, 40, 60, 80, and 100. Again, this last row here will be for our sums. Our y-coordinates, 133, 143, 153, 162, 172, and 183. So now we have our x times our y. 0 times 133 is 0. Next we have 143 times 20, which is 2860. 140 times 153 is 6120. 60 times 162 is 9720. 80 times 172 is 13,760. And 100 times 183 is 18,300. Okay, I'll rewrite that so it stays within our cell. For our x squared terms, we have 0 squared, which is 0, 20 squared, which is 400, 40 squared, which is 1600, 60 squared, which is 3600, 80 squared, which is 6400, and 100 squared, which is 10,000. So now if we add each of these up, remember we're doing just the sum of each of these columns. The sum of the x terms is 300. The sum of the y terms is 946. Sum of x times y is 50,760. And the sum of the x squared terms is 22,000. Okay? So now we can use these sums to find our slope and y-intercept. So our slope m is equal to n, the number of data points, times the sum of x times y, minus the sum of x, the x terms I should say, times the sum of the y terms, divided by n times the sum of the x squared terms, minus the sum of the x terms all squared. So substituting in our values, we have 6 data points times the sum of x times y, 50,760, minus the sum of the x, which is 300, times the sum of the y, which is 946, divided by the number of data points, which is 6, times our sum of our x squared terms, which is 22,000, minus the sum of the x terms, which is 300, it's a bad 0, 300, all squared. So if you multiply this out, you get 20,760 in the numerator and 42,000 in the denominator, which gives you a slope of 0.494. Okay, that's rounding. For our y-intercept, the same thing, just different formula. It's the sum of all the x squared values times the sum of the y values minus the sum of the x times y terms times the sum of the x terms. And that's all divided by the same numerator, or same denominator, sorry, n times the sum of all the x squared terms minus the sum of the x terms squared. Okay, so substituting in our values, our sum of x squared is 22,000 times our sum of our y terms, 946, minus the sum of our xy terms, 50,760, times the sum of our x terms, which is 300, divided by our number of data points, 6, times sum of the x squared terms, 22,000, minus our sum of our x terms, 300, squared. And so if you calculate this out in the numerator, you get 5,584,000 divided by 42,000, which gives you a value for a y-intercept, again rounding, of 133. So what that gives us is y is equal to our slope, 0.494 times x, plus our y-intercept, which is 133. Or if we go back to our initial values here, we can rewrite this as our pressure P is equal to 0.494 times our temperature T plus 133. Okay, so you can write it in your actual variables or leave it as y as a function of x. Okay, either one will work. Okay, so like I said, kind of middle of this lesson, this is the end of part 1. These questions here have data in a similar manner to how I showed it in these examples. So I recommend putting together a table exactly like I showed you in these examples to solve them, to do them by hand. And now the second part of this lesson, part 2, is going to be a separate video that looks at doing this in Microsoft Excel. Okay, because like I said, it's nice to understand what the linear regression line is telling you and how it's calculated. But for all practical purposes, you're going to use a piece of software to find the line of best fit. Okay, so that will be part 2 of this lesson. And I give you a start file. So please look at the start file if you'd like to follow along with me in Excel. So thanks, everybody.